One disadvantage of the 5R covering theorem is that if the original collection of balls cover some set, then the subcover doesn't necessarily cover the original set. Only the balls of 5 times the radius do. But what if you want a subcollection that still covers a given set, but using the balls from the original collection, not their dilations? The Besicovitch covering theorem allows us to do this, but with the trade-off that the balls are, of course, no longer disjoint, but will have bounded overlap. Let's go over the statement of the theorem. So let B be a collection of closed balls in Rd, and let A denote the set of their centers. And we're going to assume that the set A is bounded. Then there are constants C and N, depending only on the dimension of the space and not on the collection of balls, such that the following holds. So first of all, we can find a subcollection, curly B prime, of bounded overlap that covers the set A. Right? And I've written this statement in a mathematical form here using these inequalities. So let me explain why these inequalities say that the balls in B prime cover A and have bounded overlap. So this first inequality says that the subcollection B prime covers the set A. Because notice that if x is in A, that implies the characteristic function A of x is equal to 1. But now, because that means that 1 is at most the sum of the characteristic functions of these balls, so that implies that there exists B in my subcollection such that the characteristic function of B of x is equal to 1. But that implies that x must be inside some ball inside my subcollection. And that's what it means for the set A to be covered by the subcollection B prime. Now, the second inequality says that my subcollection has bounded overlap. Okay, so the reason why is suppose that I had a point x that was in C plus 1 many balls. Well, then that would mean that the characteristic function of x here would be equal to 1 for at least C plus 1 many balls. But that would mean that this sum here would be at least C plus 1 and hence exceed C, which is a contradiction. And thus, if the characteristic functions satisfy this inequality, that's equivalent to saying that the balls have bounded overlap. No point is contained in any more than C many balls from the collection. The second part of the theorem says that with this subcollection of bounded overlap, we can in fact split this collection into further subcollections, curly B1 all the way up to Bn, where each collection is a collection of disjoint balls. So let's take a look at an example. So on the left, I've generated a random collection of balls in the unit square. So the blue dots denote the centers of these balls, and the gray circles denote the boundaries of these balls. So you notice on the right, I have a subcollection of this original collection that contain all the centers of the original collection. So you notice that all the blue dots are contained in some circle. And moreover, if you pay close enough attention, you'll see that any point in the unit square is contained in no more than 4 many balls. Furthermore, this subcollection, as you can see, has been divided into 4 different subcollections, each with its own color. So you see there's a green collection, there's a red collection, there's a violet collection, there's a yellow collection. And for each of these collections, you'll notice that the balls are disjoint from each other. So none of the green balls touch each other, none of the violet balls touch each other, none of the red balls touch each other, and none of the yellow balls touch each other. So this here is an example of a Besicovitch subcovering of the collection on the left. So the proof of Besicovitch covering theorem is a bit technical. So what I'm going to do is go in a sort of high-level view of a simplified proof of the Besicovitch covering theorem, just to give the main ideas of the proof. So it first depends on some geometric lemmas, the first of which is the following. So given 2 vectors A and B, where the norms of A and B are both strictly less than the distance between A and B, then they must make angle of pi over 3 between each other. Or in other words, if we look at the spherical projections of A and B onto the unit sphere, then the distance between these 2 points is at least 1. So I won't prove this theorem, but it's sort of a fun geometric exercise. The next lemma says that if I have a collection of closed balls, B1 through Bn, with non-empty intersections, that means that there is a point that is inside all the balls simultaneously, and also such that no ball contains the center of any other ball, then the total number of balls is at most 4 to the d. So I'm not going to go over why we get the number 4 to the d here, but I'll at least explain why we get some universal constant depending on dimension there. Okay, so without loss of generality, I'm going to assume that the point that's in all of these balls is just the origin. Okay, so let's draw an example. So here I have 3 balls. Let's say this is x1, this is x2, this is x3, and let's denote the origin by a red dot, which is inside all these balls simultaneously. Okay, so you'll notice that each ball contains the origin and no ball contains the center of any other ball. Okay, so now I claim that every pair of centers of these balls satisfies the conditions of the previous lemma. So let's see why this is. So let's suppose x sub I is a center of one of these balls. Now, because these balls are closed and each ball contains the origin, that means that the distance from the centers of these balls to the origin is at most the radius of the ball. So in other words, the norm of xi, which is the same as the distance from xi to the origin, is at most the radius of the same ball, of the ball that it is the center of, which I'll denote r sub I. Now, furthermore, because these balls don't contain the centers of any other ball, that means that if I look at the distance between xi and xj, where j is not equal to I, because xj is not contained inside the ith ball, that means that the distance between xi and xj is strictly bigger than the radius of that ball. And thus we can see now these balls satisfy the conditions of the lemma, where I is not equal to j. Okay, so this tells us that the distance between the radial projections of these points on the unit sphere, so let's say this is the unit sphere, SD minus 1. If we look at the projections of these, so here's the radial projection of x2, radial projection of x1, and x3. So the previous lemma says that the distance between these red points on the boundary of the sphere are distance 1, at least distance 1 away from each other. So now consider the following sets. Let me use a color here. I'm going to find Ci to be the ball centered at the radial projection of xi of radius 1/2 intersected with the unit sphere. So this is a spherical cap. So these look like this. So this is C2, this is C1, and this is C3. Now, because the xi, these spherical projections, xi over norm xi, are all distance at least 1 away from each other, that means that these spherical caps, C sub I, since they have radius 1/2, that means that these will have to be disjoint from each other. Okay, so now, finally, to get a bound on n, we observe, okay, so let me first write, notice that if I take the sum of the surface measures of these spherical caps, okay, because each one of these spherical caps is of radius 1/2, so if sum from I equals 1 to n, the surface measures of these spherical caps are all equal to each other, and they're just equal to some constant depending on dimension. And because there are n of those, that means that they are comparable to n with some constant depending on d. Okay. Now, because these sets are disjoint, that means that this is the same thing as surface measure of the union of these spherical caps. And because this is a subset, should be d minus 1. Because these are a subset of the sphere, it's at most the measure of the sphere, and this is some constant depending on dimension d. All right, so I could compute write down explicitly what the surface measure of the unit sphere is, but rather not. I'm just going to write that it is comparable to the number 1 with some constant depending on d. And so, thus, if I trace back these inequalities, I see that the number n is at most some constant depending on d times 1. And thus, there are boundedly many such balls where the bound depends on d. So we'll just give a proof of the Besicovitch covering theorem when the set of centers A is finite. So the first step in the proof is to find a subcovering of bounded overlap. Okay, so what we do is we pick a ball, B1, let's say, and we add it to our subcollection, B prime. So we add it. And let's say this has center X1. So now we pick another ball, let's say this is B2, and if its center is not contained inside B1, then we add B2 to our subcollection. Now, we continue in this way. So let's say we visit a ball, B3, whose center was contained in any one of the previous 2 balls. Okay, well then we just throw it away. Okay, and so we keep doing this. So if we have chosen Bn, let's say, to be in our collection, choose Bn plus 1 in our original collection without the ones that we picked so far. And then if the center, let's call it x sub n plus 1, if this is in the union of the previous balls, then throw it away. Otherwise, if the center is not in the union, we add it to B prime. And then we continue in this way. Okay, so because we have a finite set of centers or a finite set of balls, we'll finish after a finite number of steps. Okay, and we get a collection curly B prime. Okay, so why does this collection have bounded overlap? Okay, so suppose X is in, let's say, BI1 intersected BI2 intersect ... intersected with BIN, where each one of these balls is from the collection B prime. Okay, well, recall that the way that we picked these balls was so that no ball would contain the center of any other ball, right? Because we threw a ball out if its center was contained in any of the previous balls that we picked. Okay, so the previous lemma, lemma implies that the total number of balls has to be less than some constant depending on D. Okay, and this is exactly what it means for this covering to have bounded overlap. No point X is contained in more than some universal constant many balls from our subcollection. So that's how we find the subcollection of bounded overlap. So now we need to show that we can take this subcollection B prime and divide it into subcollections B1 up to curly B sub n, with n no more than some universal constant depending on D. So this is our goal. So what we do first is I'm going to write B prime. I'm going to enumerate the balls in this collection. And I'm going to order them from biggest to smallest. So again, because my collection of balls is finite, this is well defined. I don't have to take supremums or anything. Okay, so the first thing that I do is I take my first ball in this collection, B1, and I put it in I create a new subcollection, curly B1, and I add B1 to it. Now I look at the ball B2. If B2 intersects B1, then I create a new collection, curly B2, and I add B2 to this new collection. Otherwise, if B2 is disjoint from, so if B2 intersect B1 is empty, I add B2 to the first collection. Okay, and I don't create a new collection. So now inductively, let's say, so suppose we've gone through the balls B1 all the way up to some Bn, and we've created collections curly B1 all the way up to curly B sub n. Now let's consider the ball Bn plus 1. So if there exists I such that Bn plus 1 does not intersect any ball in the collection curly B sub I, then we add B plus 1 to this new collection. Okay. So notice in this way, every collection is going to consist of disjoint balls because we only add a ball to that collection so long as it doesn't intersect any ball from that collection already. So otherwise, all right, so suppose that Bn plus 1 is such that it intersects a ball from each one of the collections that we've made. Then we create a new collection, Bn plus 1, and then we add little B sub little n plus 1 to this collection. Okay, so if we continue this process, this will end after a finite number of steps. So, and by construction, each one of the collections B sub 1 onward, each of those collections will consist of disjoint many balls. So now I just have to explain. So terminates after finitely many steps and obtain collections let's say curly B1 through curly Bn of disjoint balls. And also their union is the original collection curly B prime. Okay, so now what we have to do is show that this number n is at most some constant depending on the number d. So observe that if by our construction we constructed n collections, curly B1 through curly Bn, each one consisting of disjoint balls, if we constructed n of them, then what that means is that there exists some ball B in curly Bn such that for all I equal 1 n minus 1, there exists some ball Bi in curly Bi that intersects it. Right? Because suppose that there was one of the previous collections. So suppose B was the first ball we added to Bn. If there was some collection, some Bi, a previous collection, for which B was disjoint from every ball in that collection, we would have added it to that previous collection, and we would not have formed curly B sub n. Okay? So now we have this ball that intersects a ball from each of the previous generations. Moreover, by virtue of the construction, because our algorithm started from the largest ball and worked its way downward in decreasing order, that means that these balls came from further up the list, and thus they must be bigger than B, i.e. the radius of BI must be at least the radius of B, which I've denoted R sub B. Okay, so let's draw a picture of what this looks like. So let's say here's the ball B, and we know that it intersects some ball B1 from the collection curly B1. We know that it intersects some ball B2 from the collection curly B2, and so on and so forth, and then it intersects some ball Bn plus, minus 1 in curly Bn minus 1. Okay, and all these balls have radii at least that of B. So now the trick is going to be a similar proof to that lemma, that geometric lemma that we saw before. So I'm going to look at the double of this ball. So this is the ball 2B. And inside the intersections of 2B with each of the other balls, I'm going to pick a ball. So this will be B1 prime, let's say. And then I'm going to pick another ball, B2 prime, etc. And then here I pick a ball B and minus 1 prime. And these are all such that, okay, so BI prime is contained in twice the ball intersected with BI. And also I'll pick the radii of these balls to be exactly the radius of RB divided by 4. Okay, so this is possible exactly because all these balls intersecting B each have radius, at least the radius of B. I'll leave that to you to figure out the details. Okay, so now what does this tell us? So notice that if I take the sum of the Lebesgue measures, the volumes of these balls, so instead of writing curly L for Lebesgue measure, I'm going to write bars around my set for shorthand. Okay, so notice that if I take the sum of these balls, each of these balls have the same measure, right? Because each of these balls has the same radius equal to RB over 4. So that means that this sum is actually a sum of constants. So really it's going to equal n minus 1 times some number. But because each one of these balls has radius comparable to R sub B, that means that the volumes of these balls are comparable to RBD with constant depending on dimension. Okay, now recall that these balls BI prime are contained in balls from my collection curly B prime. Right, because each of these BIs is in one of my curly BIs, and that's in my original subcollection B prime. And those balls had bounded overlap. So that implies these smaller balls have bounded overlap. So that means that if I write this is the same thing as the integral of the sum of the characteristic functions with respect to, so this is I equals 1 to n minus 1. This is with respect to Lebesgue measure. Then, because these have bounded overlap, this integral is at most some constant c that depends on dimension, or the sum of these characteristic functions is. And moreover, because each of these balls is contained inside the ball 2b, this is actually at most the integral over the ball 2b of the constant c. So this equals c times the measure of 2b. And now, because b has radius equal to twice that of b, and because the constant c depends on dimension, this is comparable with constant depending on d times rb to the d. And now we see here that on this side of my inequality, I have n minus 1 times rb to the d. Over here, I have rb to the d. And so if I divide through by rb to the d, this implies that n minus 1 is at most some constant depending on d times 1. And that's the bound I wanted. I wanted to go through this proof in detail because it uses this style of argument that we'll see at least once more in the course called the volume argument, or at least that's what I call it. And the idea behind the volume argument goes as follows. So notice that on this slide, we were trying to bound the number of collections B1 through Bn. And the way that we did it was by associating to each of the sets B1 through Bn minus 1, associating a ball, so B1 prime, B2 prime, etc. So we associated to each one of these collections a ball inside 2B so that the balls had bounded overlap and had fixed volume. And then just because you can't pack too many balls of equal measure and bounded overlap into a confined space, that means that you can get a bound on their total number. Okay, and we saw this style of proof in that earlier lemma about trying to bound a number of balls that could contain a common point but not contain each other's centers. Again, what we did was that we associated to each one of those balls, we associated subsets of the unit sphere that were disjoint and had equal surface areas. And because you can't pack in too many disjoint sets of equal measure into the sphere, into the boundary of the unit sphere, that means that there must be a bounded number of such sets. And in fact, you can estimate the total number. Okay, so again, this is sort of a nifty method to be aware of. And we'll see one more example of it later on in the course. So as an example to show how the Besicovitch Covering Theorem is used in practice, we'll prove yet another version of the Hardy-Littlewood maximal inequality. Now, this one only holds in Euclidean space. However, it has the advantage that it holds not just for Lebesgue measure or doubling measures, it holds for any radon measure in Euclidean space. So again, recall that the Hardy-Littlewood maximal operator defined for a measure mu is defined as usual Hardy-Littlewood maximal operator, but now we take averages with respect to the measure mu. So again, I'm going to call this set here E sub lambda, and my goal is to bound the mu measure of this set. Okay, so again, without loss of generality, I'm going to assume that my function f is non-negative. Now, in order to apply the Besicovitch covering lemma, I need the centers of my balls to be in a bounded set. However, the set E lambda may not be bounded. But what I do is I say, I'm going to define a set E lambda r to be equal to E lambda intersected with a ball center at 0 of radius r. And now, because the limit of this set as r goes to infinity is equal to E lambda, that implies that the measure of E lambda r converges to the measure of E lambda as r goes to infinity. And so this implies that there exists some positive number r such that the measure of E lambda r is at least 1/2 the measure of E lambda. So thus, if I can bound the measure of E lambda r from above, I can bound the measure of E lambda from above. Okay, so for all x in E lambda r, by virtue of being in E lambda r, I know that there exists some ball bx centered at x such that the average of f with respect to mu over that ball is bigger than lambda. So I'm going to define my collection of balls to be the set of bx such that x is in E lambda r. And we can see that the centers of the balls in this collection are exactly the set E lambda r. Okay, so Besicovitch now implies that there exists a subcollection of bounded overlap. And such that the centers of these balls, i.e. the set E lambda r, is still covered by this collection. So now, mu E lambda, so recall that this is at most twice the measure of E lambda R. Okay, so this is at most mu of the union over the balls in the collection B prime. By subadditivity, this is at most the sum of the measures of B as B ranges over the balls in my subcollection. Now, recall that by the balls in my collection satisfy this inequality. Okay, so notice that if I multiply both sides of this inequality by the measure of Bx, or the measure of the ball, and divide both sides by lambda, it gives me that mu of the ball is at most lambda to the minus 1 times the integral of f over that ball. With respect to mu. Okay, rewriting this slightly differently, this is the same thing as the sum over B and curly B prime of lambda inverse of the f times the characteristic function of this ball. Okay, now by Fubini exchanging, or Tonelli rather, using interchanging the sum and the integral, this is equal to the integral, I'll pull the lambda minus 1 outside as well, of the sum over B and curly B prime of, I'll put the f out here, times the characteristic function of these balls. Now, by the bounded overlap property, this sum of characteristic functions is at most some constant c. So this is exactly c over lambda times the L1 norm of f with respect to the mu measure. And that finishes the proof of this Hardy-Lillard maximal inequality. So next up, we'll show yet another application of Besicovitch covering lemma, improving yet another covering lemma, the Vitali covering theorem.